3, 2. Welcome everyone to another OCP tap call. This is call number 127. Today we have Professor Camille Coti. Professor Camille Coti received her PhD in 2009 from University Paris South under the direction of Franck Cappello. Then worked as an assistant professor in Paris, and now has been an associate professor at ETS for 2 years at the engineering school in Quebec. Today's talk is about real-time environments for scalable HPCs and
Runtime
sorry,
environment, sorry.
runtime. What did I say? Real time?
Real time.
Yes, yes, I can expect that. Yeah. Anyway, so runtime environments for scalable HPC. And with no further ado, Camille, the floor is yours.
Well, thank you very much. So like I was saying, my talk today will be mostly a start for discussions. So it will be an overview. There's a few references, but it's not, about one recent result. I think it's about topics where I think we can have points for discussions and maybe collaborations with people from the community on runtime environments for HPC, because my work focuses on runtime environments. I will explain, there's a typo. I will explain what it is in this talk. So so I'm going to say what's a runtime environment, what it does, why it's necessary, and the current challenges. So the roadmap is pretty rough. There's only 3 sections. And because I'm going to list a few things that we're doing. So the runtime environment is here to support the parallel application, because we're running on distributed resources, but we want to run a single application on distributed resources. So we need something to orchestrate all these resources for one single application. So we want to start the application on these resources. We want, a high-level communication library to handle data movements within the application, but we need to support this communication library. So think MPI, think OpenSPAM, think PGAS. How can MPI perform its communications? So this is supported by the runtime environment. You want to be able to forward signals and IOs. For example, if you have a process that does a printf somewhere, you want it to to be printed on the front end. So actually, it's really a network communication. You have the process that does printf, and the data is brought to another process and printed in your terminal. So this is done by the runtime environment. You want to monitor the application. So for example, if a compute node fails, what do you do? Well, it has to be detected and handled by the runtime environment. And if there are resource failures, what do you do? So you need to detect it, and you need to take actions. And this is done by the runtime environment. So the runtime environment is a middleware that supports the application. It provides, it communicates commands. So for example, when you're starting a process, if you want to deploy a program, so if you want to execute a program on a set of resources, well, you're going to communicate a command to start the processes on the resources that are available. You want to communicate IO signals. You want to provide some portability, a lot of portability actually. So I will come back on that a bit later. But it's super important for applications to to be able to be executed on different machines, different clusters, etc. So yeah, you need some portability. You need to monitor local processes. You want to gather information, and you want to detect and tolerate failure. So you need a middleware that's capable of doing all of that. So what is it? So I made a beautiful picture. So you have the machines. Okay, you have machines that are running the application, and super important, they have to be interconnected by a network. And that's something we can discuss, but that's extremely important. This network is extremely important and extremely critical. It's important because if it's not here, nothing can happen. But it's really critical in terms of performance. So you have the processes of the applications that are running on the computation nodes, but you can have multiple processes per node. And I'm going to cut that. And you can have, I'm going to disconnect everything that can pop. Sorry. And you can have GPUs. So the application can run on CPU node, on CPU cores, and on the GPU. So it becomes heterogeneous. How do you handle that heterogeneity? So you have an overlay network that's building the communication infrastructure of this middleware, and that's supporting the execution and making it possible to provide all the features that I just mentioned in my previous slide. So I mentioned portability. So for example, let's illustrate that. So you have you want to run you have a distributed application, okay? You want to run it multiple times, and let's say you have a cluster. You want to run it on the cluster. So you reserve a certain number of computation nodes, and you execute your application. You want to run it again. You ask the batch scheduler to give you a certain number of nodes. The machines are very likely not to be the same between these two applications. And I'm only talking about running on the same supercomputer. You might want to run it somewhere else. You want to be able to run it on a small cluster. You want to run it on a supercomputer. You want to run it on your small platform that you have in your office. So the machines are very likely to change between executions. So you can say, okay, let's take the IP address and let's take a fixed port. You really cannot do that. They are going to change between applications. The hardware is likely to change because sometimes you're going to run on a machine that has a high-speed network like InfiniBand, and sometimes you're going to run on a machine that has Ethernet. So the network driver to call to perform these communications is very likely to change as well. So we need an abstraction for the network. So to designate these machines, to say, okay, I want to talk to this machine. For example, we can have a numbering scheme. So we're just naming the machines using a number. So let's say that instead of saying, I want to send this between IP address blah, blah, and IP address blah, blah, you say, okay, I want to send this between process X and process Y. So with MPI, that's what you have with MPI or with OpenSHMEM or with PGAPS languages. You have a process rank and a communicator. Well, with MPI, you have the process rank and communicator. So the translation between this process number and between well, how it's being handled by the network, how the machine is being called on the network, and how the process is joinable on the machine, this is handled by the runtime environment. So this abstraction of the hardware is handled of the hardware address is handled by the runtime environment. So practically speaking, we have when we're running a distributed application, a parallel distributed application for high performance computing, usually we have the hardware and the operating system. So that's totally classical. We have a portability layer, and we have the runtime environment and the communication library. And these two things here are the runtime system. Okay, so you have the runtime environment that's providing all of that, and a communication library that's in charge with the communications only. And the application is using that on top of that. So you have this, it's a bit thick communication software stack, but that's necessary to provide all these features. And so today I'm focusing on the runtime environment, and you can see that the runtime environment is at the same time between the application and the operating system, but also between the communication library and the operating system, because like I was just mentioning, it provides an abstraction, and it makes it possible for the communication library to work on any machine that's supported. So this communication stack is extremely critical. So I've put a picture here that comes from this paper and this presentation. Sorry, it's a presentation. So usually, how do we ensure this portability? So we have the parallel programming model. So for example, MPI, OpenSHMEM, etc. So we have the high-level communication function. So for example, MPI send, etc. And this is super portable. So how do MPI implementers do that? They actually have a portability layer that's then calling the network driver. Okay, so for example, if you have an InfiniBand network, you have a portability layer between your MPI send and the RDMA function that's being called in the InfiniBand driver. And this is in the critical path. Okay, this is really this is super important. And the measurement they provide is that they say it takes 659 nanoseconds just to go through this software stack. And the UCCS people and the Open UCX people say that they're providing this, but much slimmer. They have a software architecture that's much, that makes this stack much slimmer, and they can do this in only 70 seconds. So that's one critical work that's being done these last few years, is how can you get access from the API that's being called by the application to the network, to the hardware network, much faster. And we used to say, okay, the software traversal of the software stack is negligible compared to the time to send the data. But actually, it's their point is that it's not true anymore. Okay, I think there's a lot we can talk about here in the group because we have a lot of experts on networks that can probably have some ideas on how to reach the network much faster while being portable. Okay, so having such a slim but yet portable layer here. Also, nowadays we have heterogeneous architecture. So for example, nowadays we have CPUs and we have many cores with, multi-core architectures have been around for, okay, if I'm talking SMPs, they've been around for 30 years or so. If I'm talking multi-cores, they've been around for 15 or 20 years. Now we have many core architectures. We have heterogeneous cores. Even on my laptop has 12 cores. 4 of them have 2 threads per core. So the scheduler of my operating system sees 16 physical cores, but 4 are hyper-threaded, and 8 are hyper-threaded, 8 are not. So, and they don't have the same cache sizes, and there's a lot of things that are different between these 2 sets of cores. So now we even have heterogeneous cores on a single machine. But we also have accelerators such as GPUs, FPGAs, specialized hardware, etc. Potentially that's all together on the same node. And now we have chips that are capable of we have chips, NICs or whatever that's moving data that's capable of computing on the fly data. So for example, we have smart NICs like NVIDIA Bluefield, but there's I also heard about some project about, for example, when you have a RAID system for storage, they also have a chip that's much more powerful than what's necessary to handle what they're handling. So they want to be able to use that computation power to to process the data on the fly. So how do you program for this type of completely weird hardware that's totally heterogeneous? So task-based model seems to do well. For example, we have StarPU, Parsec, Iris, and Iris is more recent. It's being done by the people at Oak Ridge. It's task-based models, and their goal is to schedule the tasks. So you express the work, the computation in terms of tasks. You submit the tasks to a scheduler, and their scheduler is in charge with putting the tasks wherever works best. So the idea is to schedule the task there, depending, of course, on which implementation you've provided. So, for example, if you have a task and you only provide a CPU implementation, okay, it will be scheduled on the CPU. But if you provide a CPU implementation and a GPU implementation, the scheduler will have a choice and will be able to schedule it wherever it's best for your computation. And it's a very active field. There's still a lot of work that's being done. It's progressing super well. That's super interesting. They also take into account, when you're moving data. So for example, you might want to process, to perform a task on the GPU just because the data was already there. So you're saving a data movement by computing it on the GPU where the data is already, already is, etc. Another very critical point of runtime environment is process management. So I also made a little picture here. So I said that you have 2 nodes. Okay, you have 2 nodes and you have 3 processes running on each node. And the thing is that you have this little software component that I'm calling PMIX, and I'll come back later on what PMIX is. That's in charge with handling these processes. So that's PMI is for process management interface. So first you have the processes that connect to this little component, to the PMI. And for example, they exchange their contact information. They say, okay, I have access to this NIC and my contact information is that. So they declare it to the PMI, and the PMI components, the PMI processes exchange this data over the network, over over a network that's supporting the execution. So they say, okay, I'm on node 2 and I know processes P3, P4, and P5, and they can be contacted using this address, this address, this address, and this type of network. So then when processes want to communicate together, they just ask their local PMI and they get, the communication library gets the contact information and can connect and send whatever they have to send. So originally, there was PMI, which was it was an interface and, of course, an implementation that's, an interface between the pilot processes and the runtime environment. So PMI stands for Process Management Interface. So PMI originally, it was developed for MPICH, and it can deploy the processes, it can exchange the communication information, it can forward the IOs, etc. And more recently, these last 10 years, they reworked on that, and they said, okay, there are things that are in the design of PMI, or that PMI is missing, that are necessary for the exascale. So, for example, at the exascale, we say that we might have to need to combine multiple process programming models. For example, you might want a hybrid OpenMP MPI application, or an OpenSHMEM MPI application, or you want to be able to execute whatever you want to execute. So the idea is to have a process management interface that's agnostic and that can handle all the programming models available. So, for example, they support MPI, OpenSHMEM, PGAS, etc., and hybrid applications. And so to make it possible to support processes at the exascale, there are some features such as asynchronous notifications, etc., that make it more efficient when there's a lot of processes. And there are some, they call them modules, because you can add features, you can integrate the process management more tightly with whatever you have. So, for example, batch schedulers, file systems, etc. And so there's implementations of that, but it's also a standard-like specification. So, for example, if you implement this library yourself, runtime systems that rely on PMIX will be able to use your implementation because that's the same interface. So I've put a reference here about a paper that's describing PMIX if you want to learn more about it. And also, I wanted to talk about fault tolerance. That's a big part here. And yeah, it might be a teaser about the talk that Hesham mentioned that I can give in a few months. So I'm sorry, but failures happen. If you have a single computer, it might not fail. It might be super reliable. But for example, if you have a failure every 10 million hours, and you put together a lot of components, like we do in supercomputers, the mean time between failures of the whole system is only a few hours when you have about 100 or thousands of components. So even if you have components that are individually super reliable, failures are going to happen. It's not something that computation centers want to talk about because, well, it's a bit complicated to communicate on that. But Blue Waters, that was about 10 years ago at NCSA in Illinois, in Illinois. They made some measurements of that in their pre-production phase, and they had a failure every 4.18 hours. So if you had an application that was running on the whole machine and that was lasting 4.18 hours, it had one chance out of two to die before the end, to suffer from a failure. And the default behavior of parallel environment is to say, okay, if something happens, if something bad happens, if there's a failure, we're going to kill the whole application. But that's really not something that we want to do, because if you're using a big supercomputer for 5 hours and you lose all the computation that you've done, and that's a lot of computation power that's being lost. And also, if there's a failure every 5 hours or every 4 hours, you want to be able to run for a longer time. If you have a failure every 4 hours and you have a computation that lasts, let's say, 10 hours, how many times are you going to have to restart it before it can be completed? So what can we do and what must we do? We must be able to tolerate failures, because failures are gonna be the part of the normal lifespan of an application. So we need to use really resilient algorithms. So for example, algorithms that can recover from failures and that won't lose data and that can heal themselves. There are also some checkpoint restart approaches. So for example, if you have points in your application where you know that if I store this, I can restart my computation, you can insert checkpoints at some points and restart from that. Yes, that's interesting, but nothing of that can happen if it's not supported by a fault-tolerant runtime environment. So what's a runtime environment? So first, it has to be able to detect the failure. And detecting a failure in a distributed system with asynchronous communication is theoretically impossible. It was proven by Bernadette Schaumbost in 2001. Because it's an agreement, an agreement with failures on asynchronous communication is impossible. But in practice, we can do it. There was, for example, a very efficient failure detector that was published 9 years ago, 8 years ago. So I've put a reference there. And once the failure has been detected, you need to be able to survive the failure. So how do you survive the failure if you're a distributed application? So first, you need a robust communication topology. You don't want to lose connectivity. That's the worst thing that can happen. So you need something more robust. So for example, binomial graphs are an interesting topology. You can lose, if you have P processes, you can lose log P minus 1 nodes without losing connectivity. You can lose log P minus 1 links, network links. So they're robust, but they have good performance because they have a diameter of log P and a degree of log P. So you don't need to handle too many communications at the same time. You need to pull on too many sockets at the same time. At the same time, you can reach, you have a logarithmic number of hops before you can reach another node. So that's an interesting topology. And also you need to be able to maintain functionality after the failure. So a node has failed. Okay, how does your runtime environment, continue and keeps providing a decent level of service to the application? What do we mean by decent level of service? Is it a degraded mode? So, okay, it works, it can reach the end of the execution, or is it a normal mode? So it's working and it's providing some level of service. If we say that, failures are going to happen no matter what, and they're going to happen and they have to be taken into account, you want to be able to keep working in normal mode. You don't want a degraded mode after a failure. And also the runtime environment provides functionalities to the application, and they need to provide functionalities for the parallel application to recover. So 25 years ago, there was first attempt with FT-MPI for the torrent MPI. And the goal was to support dynamic resources. So if a failure happens, you lose a few processes. Okay, you shrink and you keep working with fewer processes. And you happen to be able to use more nodes. Okay, you spawn new processes and you enlarge your communicator and you can still work on the same number of processes as before the failure. So that was the first time that was really interesting. And so that the MPI people have been working on the new versions of the MPI standard for years. And a long time ago, they started working on integrating fault tolerance in MPI, and they came up with something called user level failure mitigation, which is an interface that allows you to implement the behavior of your applications to be able to recover from failures. And of course, this has to be supported by the runtime environment. So you need a runtime environment that has all the properties that I mentioned. and then to provide these applications. And then the problem of designing and implementing a fault tolerant algorithm is on the programmer side, but they have to have these features to be able to implement fault tolerant algorithms. So I've mentioned a handful of challenges that are still open, and that's super critical, highly critical in high performance computing. So that's where I would like to talk with the community and to discuss that. So how can we manage processes at large scale? How can we detect and tolerate failures? And how can we have portable and low latency communications, for example? So usually the approach in the MPI community is to be as portable as possible. So um, for example, there are some networks that can handle broadcasts and multicast. And we're not using that because we say, okay, this type of network can handle that. But what happens if tomorrow I'm on a different kind of network? So we're not using it. But I think, based on the discussions that we have on the WhatsApp, on the WhatsApp group, for example, I think there are things that services that the low level layers can provide to make these kind of things easier. Same thing for failure detection, same thing for low latency communication, same thing for we had a short discussion on the WhatsApp group on measurement. There's Kevin's video about clock synchronization that's super interesting when we want to synchronize processes in a distributed application, etc. So that's it for me, and I would be super happy to talk with you.
Great. Let's open the floor for questions, I guess.
Yeah.
Right.
I have a question, Camille. Have you read the paper by Dong Zong and others from the innovation lab in Knoxville University?
Oh yeah, I know this paper.
Yeah, because they have this Turing machine award winner, Jack.
Yeah.
The paper is runtime level failure detection and propagation in HB systems. Sounds like that is similar to the one you mentioned before, right?
Yeah. But it was around 2005, right?
This one is 2016.
Yeah, but the previous one was no?
2000, the first one you talked about.
Yeah.
I can tell you which year, because I have it actually. Let me check 1 second, please. The one you cited,
It's from supercomputing 2016.
the one I just mentioned is
Yeah.
16, yeah.
Yeah.
But so failure, the one which is failure detection and propagation in HEB systems.
Is it by Xingzong Chen?
That is one 2016. This is George
Oh yeah.
Bozilica.
Yeah.
That is 2016. Yeah,
Yeah. That's the one I'm citing.
exactly. But
Yeah.
there is another one which is maybe earlier. There is lots of work came out from this group in University of
Yeah.
Knoxville. Lots of work.
I spent 2 years there during my PhD.
Really, that's excellent. That's excellent. Very good group.
Yeah.
Very strong.
Yeah.
And Jack, the Turing Award winner, he has a book about HPC in heterogeneous environment.
Yeah.
He has the whole book. I have the book actually. I haven't read it
Oh,
all, but there are good chapters in it.
okay.
So each one of those is a subject, Camille.
Yeah.
You can have a presentation about it. You know,
Yeah. Yeah.
these are good subjects, very interesting subjects. If you are interested, I can work with you on one of those. And we can have a joint presentation if you want to.
Okay.
To
Yeah.
speed things to speed things up.
Yeah. So yeah, so that's why I wanted to give this very open presentation about me. Yeah, we have many subjects that are open in the field of runtime environment. So that's very interesting distributed applications, I think.
100%.
Yeah.
Right.
Yeah, excellent presentation. Thank you. You've hit the nail right on the head. So I'm delighted to see that you're doing this work. We've been working in this area, at least for 20 years now. And my last job at Apple, which wasn't that long ago, was to figure out how to boot and manage 1 million machines and how to debug systems on top of that. We were successful in several ways. We got Apple to convert to Docker and move away from some of the last rider wins styles of APIs, which we know don't work. But the thing that we've discovered since, and we've got quite a lot of work on this, is that if you don't have causal connections at the Ethernet layer, right down at the lowest hardware layer, you have to have pairing. This is the reason why I've been involved for the last year or so in OCP TAP, is I've given several presentations that basically make this point. If you don't have an acknowledgement on each link for every packet, and it needs to be not just lost acknowledgements or lost, it's about incompleteness of the sequence of pairings. And this is a back-to-back Shannon model. We do have a paper coming up which is going to describe that. So what we realize is that the Open Fabrics, for example, hides all of this. It's a black box down in the hardware layer, and you can't hide it. Basically, if you're losing packets or you're losing what we call temporal intimacy at the lowest level, all bets are off. You cannot recover that Shannon information at any higher layer.
Yeah, so that's you mentioned the Open Fabrics people, and I think so. When they first started releasing drafts for ULFM, I asked George why one-sided communications were not included in the draft, and he told me that the Open Fabric said that it would be too expensive. Like you mentioned, if we enable that, we need to acknowledge everything, but do you want to enable it all the time and lose some things in terms of latency? But also, when the runtime environment is in charge of detecting the failure, it's being done, asynchronously from the communications, because either you perform a communication and you see that the target process is dead. This is done at the communication library level, or you run you try to do your communication, whatever happens. But somewhere else, the runtime environment realizes, oh, this process over there seems to be dead, and we're considering it dead. But we don't know which communications have succeeded and which one are basically lost in a black hole. So that's a bit more difficult. Well, that's a lot more difficult for the programmer to program that, because they don't have, they know that a failure has happened, but they don't know when it happened. But I think it's one way to dodge this acknowledgement problem.
So we have seen for several decades now, the only choice that programmers are given is basically to do a timeout and retry. And what we also, and I've been involved in many large data center systems design. We are fundamentally a software infrastructure company, so we don't compete with hardware vendors, but we are trying to solve exactly this problem in the Open Atomic Ethernet, which is one of the work streams of this project. And we are having exactly that conversation next Wednesday on this argument between latency and bandwidth. And what we've discovered is we go all the way back to the original Xerox PARC documents and to Bob Metcalfe's PhD thesis and to the original Ethernet paper. And there is an assumption there, which is true when the links are very long, that you are wasting bandwidth if you can't push multiple frames down on the wire at the same time. It turns out that all of those dimensions of thinking were applying to much slower networks with much longer cables. And so what we're working on is the idea that if the cables between each of your nodes is less than, say, the length of your arm, then you've still the packet itself is going to be like 1.5 meters. So you've still got the packet coming out of the SERDES in the transmitter, while its head is going into the SERDES, into the receiver. And so you've now got an opportunity to do an entirely different solution of solving the Shannon capacity theorem problem, and always to guarantee that your packets are never, not only are they never lost, they are, if they are lost for any reason whatsoever, like for example, someone cuts the link stops. And everyone will say, oh, but you can't have that. You must get it going again, do a retry. And so we have all of this mechanism that goes all the way up into the application to try and do these successive retries. And I experienced those in some large data centers we had before, and they just result in a cascade failure. You get retry storms, you get reconstruction storms, you get what we call it these days, metastable failures is the latest name for this, but we used to call it limpware. And there's what we've realized is that there's something very profoundly important about that decision that was originally made in Ethernet. And if your packet is like, say, let's imagine you're using a 64-byte packet, and you calculate with a header how long are they on the wire? 1.5 meters. So, and that's at 100 gigabit lanes. So it's okay. So there's a different way of thinking about this problem.
Yeah.
So this is why we started the Ethernet 2025 workshop in January this year at the Chiplet Summit, because you can't ignore this problem at chiplet scales. Or when I say chiplet scales, I mean chiplets, modules, motherboards, and motherboards talking to each other inside a single rack. We're bringing together experts from the database and distributed systems community to actually work on exactly what primitives would you like to see in Ethernet for the next 50 years.
Oh, that's really cool.
We'd love to have you in some of our meetings. I'm going to put this particular recording on our wiki. I put the link in not of the wiki. I put the link of the project in the chat here. But what's fascinating is that you have come up with exactly the same kind of perspective on this elephant that we're trying to solve in distributed systems. So well done. Thank you.
Thank you very much. That's super interesting. I'm going to keep an eye on that.
Sorry, I don't want to hog the floor, so let me shut up for a bit.
All right, anyone else wants to add something? Maybe I can ask something. So let's say in all these processes of runtime and let's say you are actively like let's say running threads and so on. How about the opposite? Let's say if you just want to observe thing, like let's say analytics, how would you basically change things or modify things, or actually keep the same thing and just like look at it from a different perspective?
You mean analyze the performance at runtime?
Yeah, basically you're looking, I mean, simply speaking, like you're looking at, let's say, hardware utilization in a node, or you look at hardware utilization in a cluster.
Yeah. So because usually when you're doing performance analysis, you're doing, well, the traditional approach is by doing it post-mortem. So you run your application, you're collecting data on what's running, and you're collecting data from, hardware counters, etc. And eventually at the end of the execution, everything is put together and you can observe and see what's happening. And so there's a challenge there. Well, there's a few challenges there at the exascale, because you need to be able to gather the data, and we're talking gigabytes of data if you're collecting everything and all the time. You want to put that together, so you need to interleave all your traces. There are some visualization challenges, because how are you going to take a look at, I don't know, hundreds of thousands of MPI ranks plus threads, etc. So there's a few challenges there. So one approach is to say, we're not going to analyze everything. So you want to select the metrics that you want to look at. You want to select what you're going to analyze. So for example, you might not want to analyze all the MPI calls. You might not want to analyze all the pthread calls. You want to do selective instrumentation. So for example, I'm the maintainer, the developer and the maintainer of a compiler, an LLVM plugin for Tau that allows you to to ask the compiler to insert measurement points in your code. So you're only analyzing whatever you want to analyze. And there are some exascale applications that have taken advantage of that to tune the application, because it was not possible to do it before, because the trace was so big that taking the measurement was disturbing the measurement itself. So the other challenge is to say, okay, I don't want to look at what's happening at the end of the execution, because that's too late. I want to look at what's actually being done. So I want to do real-time monitoring while the application is running. And that's something, there are some works about, taking metrics. So you have to have an infrastructure that's collecting data and you're displaying it. So we're talking about performance analysis, not monitoring, that system administrators use. And there's still a lot of work to do in that area as well.
So like I like to look at it this way. Let's say you have your workload, let's say represented with, let's say, Markov chain of like going from states to states, let's say for like, different, like as you basically progress through something, I mean, I really want to treat it as like a black box. Like
Okay.
you have something that is running there, and then you have a first level approximation, or second, whatever, that
Okay.
you turn it to a Markov chain. And
Okay.
then the Markov chain, it describes like from this state you go to this, from this you go to that, whatever is predictable, right? And again, because you're doing it like post-causal, so it is you're just looking in the past, so everything is tamed. Then you look at your system, and your system, even though I'm tempted to look at it also statistical, but I look at it as more like of a FSM, where this FSM has can host certain capabilities, and how much resources my Markov chain takes to use this finite state machine is going to be basically my utilization. And I'm not talking about just a scalar anymore, that like, oh, 100% CPU, but hey, you left the RAM, oh, you left the network, you left like the GPU, all of this. So it's like a multi-scale thing. Now,
Yeah.
when you fit this in, you will not only understand, it's like it's literally, I'm trying to still wrap my head around it. You don't have just a scale that you say like, oh, so much percentage of usage or something. You will basically measure against utilization of your system at large. This is not a node. This is, I mean, you can
Yeah.
look at it as a node with multiple resources, but you can look at it multiple nodes in a cluster. And you look at a whole potential of like how something can work, and then you translate that back into how, like a bunch of recommendations, how you can actually get more. Let's say I mean, you may have recommendations that they're meaningless, of course, but you may have recommendations that they can lead you into something, because you look at something from a high level. I don't know, like I'm still like trying to figure out this, like I'm taking a top-down approach, so I have just the idea, I'm trying to fiddle it into it to bring it down to something that can be meaningful. And I speculate, my expectation is it's not gonna go anywhere. So if I get anything out of it, I'm happy.
Yeah, that's a funny question. I don't know about works that that focused on that. That would be super interesting. It's a way to see and to look at the utilization of hardware resources in high performance computing, probably in other areas, but where performance is and resource usage is critical.
Yeah. Bijan, you want to add something?
No, not really. I just I was looking at I was late to join. I have conflict, I'm sorry. But I on the topic I just posted in the chat, there's another group, Paul's group is excellent. There's another group that's working on a slightly different problem. They're working on polymorphic architecture and polymorphic architecture runtime. So I put the link of the group in the chat if you're interested. And then they also, I could send you in this chat a couple of, expository papers that they had done just to kind of ideate and define what it is they're working towards.
Yeah.
So
Thank you very much.
one of the things going to Ahmed's question here, the whole concept of Markov chains. I put the link in the chat of the actual paper, but I did a fairly thorough analysis of this recently. I did it the old-fashioned way. It's a fairly recent paper. I actually read it line by line, equation by equation, and it took me 2.5 days to actually grok everything that was going on. But this is a really important issue, and I want to highlight that the premise behind Ahmed's question about Markov chains is it basically implies that you're only thinking forward in time. And the problem is time is this ephemeral thing that's like up in the sky somewhere, and it doesn't exist. Modern physics just doesn't give you a notion of causality or of time. But the proof in this paper actually proves that this whole Markov backwards and forwards thing actually is mathematically significant, because it basically says that each node, when it's receiving information, is always going to think that that notion of time, I'm going to put in quotes here, is scare quotes, is really is an observer function. When you look at the bigger system of the ontology between communication between Alice and Bob on, say, an Ethernet link, it turns out that that paper absolutely nails it on the head. And I think it's called Emergence of Opposing Arrows of Time in Open Quantum Systems. Now, what I'd like to do is to bring the physics community together with the computer science and networking community to actually teach each other the problems that they have and the solutions that they've already discovered. So I would recommend anyone to read that paper, and I'm happy to send you my summary of the actual analysis that I did.
Wonderful.
That's a blast from the past. I was responsible for doing the Markov chain analysis for telecommunication systems back in the 90s. And you're absolutely right. It's the discrete state transition was all we could imagine back then, but now we're looking at it like, okay, well, there's something wrong with this definition.
My initial training was I'm a telecommunication engineer, and my Markov chains teacher worked on the quality of service in ATM networks.
Yeah.
And she was also in charge with setting the traffic lights on a highway, well, on a major street next to Paris. She used Markov chains for that as well.
Same
Because
problem. It's the same problem.
Yeah.
Yeah. I like to look at Markov chains and state machines and state space representation and transitional matrices all the same. One statistical, one continuous, one discrete, one crisp, you know, and have them all related to each other. I mean, they are related to each other.
Yeah. So the insight that we have is that we're trying to emulate something called the no cloning theorem classically, which we know has been proven now. You can do it classically, but the no cloning theorem is a very fundamental aspect of physics. It's literally the machine code of the universe we live in. A lot of people think the no cloning theorem is all about you know, eavesdropping on quantum key distribution and so on, but it's not. It's actually a foundational problem, or a foundational tool rather, to guarantee exactly one's semantics, which, as you know, Camille, is the gold standard for distributed systems.
Yeah. Okay.
All right. Any more questions or comments, or maybe I can pull Kevin's legs here. Like, Kevin, I have a question for you. I mean, it's kind of related as well. Can you give us a brief? How is the CPU usage percentage basically calculated on a given CPU?
Oh, so it depends on what you want to be looking at. But the idea is to say, okay, the maximum, what we call the RP, the Rmax, is the theoretical maximum. So how many instructions can your CPU handle in a single cycle? So it's 2, 4, 8, etc. Multiplied by the width of a register, multiplied by the number of cores, multiplied by the frequency. And your computer will never be able to go faster than that. And then you run a benchmark and you compute the ratio.
So basically, this is a number that it's not a register you pull from the CPU. So you're looking at something you observe, right?
You're looking at the theoretical number of operations that your CPU can do in 1 second. Theoretical. And so you're really taking everything that your CPU can do, and you multiply, you compute you compute everything that it can do in 1 cycle. There are sources of parallelism inside of your core, of each core, and there are multiple cores, there are multiple CPUs on the machine, and that's very much, yeah, that's completely how much your CPU can compute in 1 second. You multiply it by in one cycle. You multiply it by the number of cycles per second. That's the maximum that you can reach. And then you run a benchmark, and how, the ratio between the maximum and the score you get from the benchmark is the CPU utilization. So why are you slower? Well, it's always because of data movements. But there's also some metrics that you can get. So for example, there's a hardware counter that's telling you how much CPU cycles you're wasting by being stalled, waiting for data to be available. And you can do some very fine-grained measurement like this to know why you're slower. And sometimes you can just say, okay, I'm slower. There's nothing I can do with that.
Camille, you said telecom, so I'm gonna push back and say Erlang C.
Yeah.
Wonderful. All right. So I think we got 4 minutes. We can give that back to you. And Camille, please share the slides with us so we can put them all back on the wiki alongside with the recording.
Okay, I will fix my typo and I will send it on the WhatsApp group.
Wonderful. Wonderful. All right. See
Thank you very
everyone
much.
in 2 weeks. And thank you very much again, Camille.
Thank you very much.
Bye.
Bye.